Okay, assalamualaikum and good morning, everyone. So today we'll have our second lecture of the week. So, but today I want a favor from you guys. I'm experimenting with the faculty's Wi-Fi. On Monday it was unstable and I got disconnected twice. So I will try again today. Hopefully it has stabilized. So inform me if I get disconnected. Okay. So okay, right, great. So okay, I'll start the lecture now. So we've gone into power series at this stage from the first chapter, and so instead of having sequences of numbers, we are going to have sequences of powers of a variable. So we have actually discussed about that, and we've gone through the example of a power series for sine x and how we use taking derivatives of the power series expansion, and then you'll be able to get what you call the coefficients that you have over here, which are unknown. Okay, and then once you do all the derivatives, you'll be able to determine see once you do all the derivatives, all the coefficients of the power series expansion of sine x. So today we'll proceed, okay, because sine x is really the power series that you see for sine x is really what we call a Taylor series, or in this particular case it's called Maclaurin series because we expand about the origin. Okay, so one can here's a simple exercise for you to do is to do the same technique to the case of cosine x. Okay, so you can try this for yourself and then compare it with compare it with some standard table of power series expansion for cos x. I believe you have seen it before, probably in some other basic maths course. But if you have problems, one could use a tool which is freely available on the web, okay, which is called Wolfram Alpha. Okay, so I hope everyone has seen that before, but you have not. Let me just show you. So here's Wolfram Alpha web page. It's wolframalpha.com. Hopefully this works. Can you see the web page? Somebody? Okay. So Wolfram Alpha is a pretty interesting technology. Okay. Yes. No, it's basically you. Somebody getting in. So yes, there's a powerful server somewhere, stored somewhere, and one can actually interact with that server, asking questions. Usually it's mathematical questions, but you can ask almost anything. Okay, so I'll give you an example over here. This is a standard example that I've whenever I introduce Wolfram Alpha to students, I use this. Just you can write your questions in ordinary language. Okay, so for example, I can ask, what is the distance from my home from Seremban to Kuala Lumpur? So it's perfectly, no, it's an ordinary sentence. And then when I submit this, the server over there will try to interpret it. And to interpret this, it requires essentially some kind of artificial intelligence, and because you're asking in a language which is not really familiar to the computer. So it has to process that question using AI. And let's see. So it's calculating now, or trying to find the answer. And you'll find that, okay, distance from Seremban Negeri Sembilan, no, you even know where Seremban is 56.46 kilometers. Okay, so that's, so roughly I'll come to work. Maybe, I'm not sure whether he knows University Putra Malaysia. Let's see. So you probably know. Okay, so he knows it. So I travel every day about 42 kilometers per day. To and fro, that means I travel about 84 kilometers. Okay, so I come every day. So within a week, 84 times 5, and you can see how much I travel for a week. Okay, and it also gives you another gives you in centimeters. Of course, you don't really use it, but you can also talk about, okay, if I were to drive in a car, you would try to estimate which with this particular speed over here, I'll take about 28 minutes. I normally take about 40 plus minutes, really. Okay, and then if your sound, okay, you only need 2 minutes and 3 seconds, and your particle of light in a particular, say, telecom fiber, for example, it just take you 195 microseconds. So you get all this wonderful, what you call, wonderful information from this Wolfram Alpha by just asking this question. Somebody is coming in. Please shout if there's something that you want to ask. Or let me just do another thing. Let's say chemical properties of give me a compound, carbon monoxide. Okay, never mind. So we'll give you all these properties of carbon monoxide, for example. Okay. And so in other words, all these things are available for free. But of course, if you ask for more details or you want to download the page, then you have to subscribe to it. So you have to pay certain amount per year, for example. Then you can actually download the page, and then you can do more elaborate what you call queries to this Wolfram Alpha. Okay, let me just do another one. What is the weather temperature, say, in New York? Current, let me put it current. And you will access some database somewhere about the weather, okay, and it will probably tell you. Okay, so it's about 15, about 15 degrees Celsius. So I think now it's probably about autumn. Okay, so okay, Now the point why I want to introduce this Wolfram alpha, you can use this to do your homework. Okay, help. Okay, you have to understand so that you'll be able to understand the answers. Okay, for example, now I can ask you what I ask you to do: power series of cosine x. There you go. Okay, so you get all these even powers of x as your power series for your cosine x, and then the general form is actually given below. Okay, so you can do wonderful things with Wolfram alpha to help you do your homework, but again, it's not meant to be something that is supposed to aid your understanding rather than remove your understanding. Okay, so it's not supposed to help you not to understand. You need to understand the theory behind it. Okay, so you can use that to do your homework, for example, later on. Okay. Now, so let me go to the idea of Taylor series. So the idea is like the example that we gave for the sine function. The sine function, we know that is a smooth function. Okay, so that means no matter how higher order derivatives that we take is always well defined. So if you assume the function is actually smooth, then one can do the same for any function. Okay, so here is what we do. We assume there's this smooth function of f of x, okay, with this power series, and it's expanded about an arbitrary point. So in the previous case for the sine x, we use x equals 0. Here we make it up slightly more general, so this is an arbitrary point, arbitrary specified point, and essentially what happens in this particular case, you don't just have your x's, but you have your x minus of that point. Okay, so you expand it in terms of powers of that. So here your function f of x, first you have the zeroth order term, which is x minus a to the zeroth power, which you know equals to 1, and then to the 1 power, second order power, quadratic power, then cubic power, and so on and so forth. Okay, so again, the technique requires you to find out what these coefficients are, and we can do this by taking derivatives, just like we did for the case of sine x. Okay, so when we do the derivatives, for example, for f of x, the first order derivative is given here. So you can see what happens in this particular case. This one drops out, and then this one becomes the constant term, and then you have all the other powers of x minus a. And then for second order derivative, then this one drops out, and this becomes your constant term, and so on and so forth. Okay, until you get to the nth order derivative, then you have your an multiplied by some numbers, okay, to be your constant term. So now what one can do, in order to get rid all the other terms over here, for example this one, okay, you just substitute x equals to a, and that will give you 0. And then you substitute your f of dash of a here. Okay, the assumption that you need over here is that you know what, so your f of x is actually known. Just like your sine x previously, you know what sine x is, and you can actually use a table or you use a calculator to find out what's the value of sine x at a particular point. Okay, so here the assumption here is you know what this function is, but you do not know the power series. Okay, so here once you substitute x equals to a, then all these powers drops off, and then you'll be able to determine your coefficients. So finally, once you do that, then you will see that, okay, I get this coefficients to be just simply functions evaluated at a, or the derivatives evaluated at a. Okay, and finally you get to this particular formula, which is your Taylor series of your function of f of x expanded about the point x equals to a. Okay, so that's how. But again, just to remind you, the assumption made here is that your f of x is smooth, so that you can actually calculate all your derivatives for that particular function. Okay. So this is called series. Is there a question somewhere? Please inform me if somebody is getting in. Okay. Where was I? So, right. So this is called Taylor series. So if you pick your specified point where you expand the power series about, okay, to be simply your origin, that means you picked up e equals to 0, then it's really called a Maclaurin series. Okay. So just another simple exercise. Now that you have a general function to be expanded in terms of this Taylor series, you can recheck what you have done for your sine x and your cosine x before. Okay. So, but really for physics, those who are trying to analyze results, experimental results, or doing some calculations in theoretical areas, you are really expected to know certain standard Taylor series. So here is some of this standard Taylor series that you need to know. This is for sine x, okay, and then you have your cos x, which you should try to do, and of course you can do for exponential. And one nice thing about your exponential here, you can see that you have all the powers of x, okay, only to be divided by this factorial thing. Okay, for the case of sine x and cos x, sine x only have odd powers, and then cosine x has only even powers. Okay, and there's a reason for, if you remember, there's property of sine minus x equals to minus sine x, right? And this follows from the power series, because minus x to the odd power is always the minus sign. Okay? And for cosine, for example, is always even. Okay, so in other words, you put minus x to the even power, is what gives you the same sign. Okay, so these are some things that you're probably able to find out what it is. Okay, by using the symmetries of your function itself. Slightly, so all these sin x, cos x, exponential x are things that you should know by heart. So you don't, in other words, you don't need always to what you call calculate it. No, you're supposed to, okay, what's the power series of cos x? Okay, I know what it is. You just write it down. Okay, so this is expected of you in some sense. Okay, exponential x is another one. Log 1 plus x is also another what you call natural function that you find in physics, and because of that, sometimes you need to know it by heart. So if you do not know it by heart, then you probably have to calculate it. Okay, so if you can memorize it, it's much better. But if you can't, there's no real need. You can always use the technique of Taylor series to do it. Okay. The other one is probably what we had so far are all what we call infinite series, because your powers of x goes to infinity. But one could also have the case where your powers of x are terminated at some what you call some finite power. Okay, and usually this is through some binomial, using some kind of binomial expansion, and I believe you have seen this in high school, at least I think, at least for the square one. But you can actually multiply it again and again, and then you'll be able to find the binomial expansion. So here are essentially your coefficients over here. And these coefficients are normally what you call written in this, so what they call this, n p choose n, right? This is in high school. Can somebody confirm? You have this notation before? Am I? Okay, good. Because nobody's giving feedback. So, did you see that kind of n choose p choose n thing? Have you seen it before? Great. Okay. That's all. That's all I want. Just yes or no. I don't want elaborate things too much. The definition is also denoted as this bracket of Pn, and the definition is just given by this p factorial divided by n factorial times by p minus n factorial. Okay, so this is called binomial series, and I'm pretty sure that you have seen it quite a lot. So, but you can extend your binomial series to usually what happens, your binomial series, in a sense, you consider your p here to be integer, right? But you can generalize this a little bit more, positive integers usually. So here's an example where your p is not a positive integer but it's a negative integer, and you can still use the, somebody getting in? No one? So you can still use the formula for the binomial, and the way to do it is to just simply use it without really thinking. So you remember what it is. So Pn is what? Pn is p factorial. What was it? I can't remember now. P factorial, yeah. P factorial. And then n factorial, and then p minus n factorial. So what do? We always, you can see that, okay, your p factorial here, if you were to expand this, without the denominator, then you go go from you multiply p until 1, right? But it will get cut off at this n factorial thing, so you just p until I think n plus 1, okay, and then you have to divide by p minus n factorial. So you do the same kind of thing. So for example over here, this will be what? This is minus 1 n, okay. So let me just see if this is correct or not. So in this case, let me just do the first one. Let's see whether it comes out right or not. So I would actually have minus 1, and then it should stop at what is p is minus 1, right, and then n is 1, so minus 1 until 1. Just hang on a minute. 1 factorial, let me do this properly. 1 factorial and then minus 1 factorial. Then I will have minus 2 factorial, which is not what I want. Hang on, how should I think of this? Okay, maybe it's not generally. I thought I made this clear, so it might confuse you. Okay, the problem is this minus 2 factorial. So you don't really want that. Hang on. What is 1? Okay, maybe not. So I think let me just delete that. Okay, but the idea here is now you should be able to expand at least the numerator. Okay, it should be generalizable somehow. I can't remember how I did it. At least you can what you call expand this. So for example, minus 1 factorial, you just have minus 1 there, and then minus 2 factorial, then you just have minus 1 minus 2, and then you go on. Okay, and then this 1 factorial is there, 2 factorial is there. Okay, so I'm not sure about this. Okay, so probably it needs a little bit of modification there. So anyway, so in other words, you by right, this idea of binomial expansion can also apply to this to numbers which is negative integers. Maybe you can check for the case of minus 2 if you want, and then you try to check. Okay, you could also check here. Here's an exercise. You can actually see that the signs here over here are alternating, positive, negative, positive, negative. But you put this is the expansion of 1 plus x at the denominator, so you can actually replace it by 1 minus x, and then you should be able to see that this gives you all the positive sign. Okay, so not only just negative integers, you can also do this for the case of again there must be some conditions over here. Can't remember precisely what. So here is the case of p equals to half. Okay, so again you expand it. Okay, in this case you just multiply for the first one half. Okay, and then half times half minus 1, and then half times half minus 1 times half minus 2, okay, and so on and so forth. Okay, so you get your binomial expansion for your square root. So let me see what's the conditions for this later on. Probably I have to check. Okay, somebody coming in. Did somebody want to say something? No? Okay, so these are some of the things that you can actually do. The other thing for here is a formula for the case of half choose n, or no, there's a half n here, okay, and you can try to get a closed form for this, and you can write it in terms of this, where I introduced this idea of double factorial. What does a double factorial means? The double factorial means, for example, if it's an odd number here, then you just multiply the odd numbers after that. If it's even powers, then it's even if it's even number, then you just multiply the even numbers. Okay, so that gives you the idea of a double factorial. Okay, and one could really also define. Okay, so this is the definition. Probably the general definition is this. Okay, this is more right. So this is general definition. So you can extend this to any number that you want. For example, alpha to be real. You have seen it in terms of fraction. You can actually make it real, and then you just simply use this formula to get your binomial expansion. For that, let's say square root 3, for example, 1 plus x. Then you'll be able to find out what it is. Of course, it will be messy, of course, because you take square root 3 minus 1, square root 3 minus 2, and so on. Okay, or you can even you can have it as a complex number, but we'll learn about complex number later on. Okay, right. Okay, what else do we need to say? Okay, so these are just using your Taylor series. Okay, and then for the case of the finite power expansion, then you use your binomial series. Okay, so generally you can try to get more power series by using some manipulation. Okay, for example, you can actually multiply two different functions, and then you get your power series for one function with power series of another function. So here is the case of a polynomial. A polynomial is already a power series. Okay, for example, x minus x. Okay, and then you multiply with sine x, then you multiply with the power series of sine x, then you get the power series of this whole thing. Okay, you can also not just multiply polynomial with power series, you can multiply power series with power series, and this would be helpful to do in some for example, in some calculations. Okay, you don't need the whole function itself to do certain calculations. This is particularly true when you use some kind of a approximation with respect to the function. Okay, when you use a computer to calculate certain things, then it's good to know at least the first few powers of your power series. So, okay, the skill that you need to know from this, oops, it's not appearing. The skill that you need to know is to write down the first few powers of a function. The first, should really say it differently, write the first few terms of your power series. Okay, so that would that is expected of you. Okay, so you can do a lot of exercises for this kind of things. Not only can you do multiplication, you can also do division. So here's an example. You have this x to the power minus 1 times log 1 plus x. You know what log 1 plus x is, and x to the power minus 1 can think of as a division. And you can simply divide by x, and the answer is quite simple, and you get the power series for that. But sometimes you can even do much more what you call elaborate than that. That is just dividing by x, but you can divide it by some power series. For example, an example given here is your tangent x. So your tangent x, if you remember, this would be equals to sine x divided by cos x. So what do? You take the power series of sine x, divide it by the power series of cos x. So this is your power series of sine x, this is your power series of cos x. So what do? You see, okay, how do I do the division here? Well, in order for me to get an x over here, what do? I need an x multiplying at least this one to get it, that x. So I have to multiply x to that, and that will remove this x, okay? And then x to this one, that will give you x cubed. X to this one, that will give you x to the fifth, okay? And then you essentially subtract this from the original expression, okay? And then you do the same again and again. So finally, now if you try to do it properly, then you should be able to get this power series expansion for tangent x. Usually it's a bit, this one is a little bit difficult to memorize, okay, but no, again, this is a familiar trigonometric function that you often use in physics, okay. Again, this is just another demonstration of your division here, your binomial series. So you can think of to power minus 1 here by just 1 divided by 1 plus x. And then you can do the same thing again over here. So here's your 1, you divide by 1 plus x. And then in order to get the 1 there, I need a 1 to multiply 1 plus x, and then you have the remainder and things on. Okay, I hope you know how to do it. The other one would be substitution of a polynomial inside, say, a power series. Or here, for example, I have your exponential here. Okay, I know how to do a power series for exponential, but now instead of just exponential x, I have an exponential minus x squared. So this is a polynomial to second power. So I can write this, well, I can rename this minus x squared by u, then just simply write your exponential u here, but then you replace your u by minus x, and then you get your power series. Okay, what is this? Right, here's another, this is a bit more complicated now. Again, sometimes you have this kind of function to appear in some integration, exponential of tangent x, for example. Again, you use the same technique. You write your tangent x as u, then you expand it, and then your u will now be replaced by tangent x, but your tangent x has an expansion that you have seen before, okay, which is that. So again, this is a bit much more complicated because you have this not so uniform kind of power series like the one you see for sine or cos, but you have all these different coefficients that you need to multiply. So you have to do this carefully, but again, sometimes you are asked only to do, say, please expand exponential tangent x to, say, 4 terms. Then what you need to do is just to look at the 4 terms that comes from those expansion there. Okay. Right. Okay. Here's another interesting thing. I believe you have come across the idea of arctan or arcsine or arccos. You know what that means? A little bit. So what does it mean?
Inverse tangent.
Right. So what do you do to find out what the function is? So he asks you, okay, give me arctan something. How do you evaluate it? What do you do usually? No answer? I'm pretty sure you have uh, come across it, so you need to evaluate it. Then probably you need to use a particular table or you use a computer, right? Hello? Everyone seems quiet. So let me just do something here. So you can always do this. Let's say I want arctan 2. You already give me the answer. Okay, so you can get all these horrible numbers there. Okay, right. So normally nowadays you have computer programs that do for you. I'm not sure the calculator can actually have that these days. Have so long have never used a calculator before, so I do not know how complex the calculator nowadays. But I think probably has come to the point of there is a function that can just simply plug in arctan and then the number. Then you can actually calculate. But what often the case is actually you can use it using integral. Okay, so this integral is actually equal to arctan. So if you still remember what you do in this particular case is to think of, okay, what do I need to do in this particular case? Somebody coming in? Okay, where was I? What was I trying to do? Oh yeah. So if you remember, what do we do in this particular case when you try to integrate? Okay, close that. You do it by substitution, and then you write t equals to tangent theta, and then 1 plus t squared is 1 plus tangent squared theta, and you can evaluate that to be your secant squared theta, right? And then what would be dt? dt will be what? dt will be tangent theta secant theta. What was it? What's the derivative of tangent theta? Let me go to Wolfram Alpha. I can't remember my calculus now. Dx of tangent x see, I can't remember my all the simple things anymore. Just use a computer. Or secant squared, sorry. So that will give you a secant squared. Go back there. So this is wrong. This is secant squared theta d theta. And then you can see that this is secant squared theta d theta. This is secant squared theta. Okay, so if I have something like that as your limits, then over here it should be your arctan. Okay, so that's why you get your arctan written in terms of this particular integral. And you can do the same for arc cos and arc sine. Then your denominator will be something else. Okay? So your arctan x is just the integral of 1 over 1 plus t squared. And I know how to do power series for that. So it will become that. And then now I can just simply integrate each of the terms. And then I will get my power series for arctan x. Okay. So these are things that those techniques you should know. This one is integration. Of course, the other one is to do differentiation, but differentiation is much easier. Okay. What else? Okay. This is the expansion of your Taylor series about some non-zero point. So, for example, earlier we had this log 1 plus x. Okay, the log 1 plus x is given in terms of this power series, and that is expanding about x equals 0. Okay, so yeah, I'm trying to say, yeah. So now, suppose I'm given the question here that I want to expand log of x. Okay, and then the expansion is supposed to be x equals to 1. So what do I do? This is already a prepared question in some sense. What do I do? Log x, I can rewrite your log x as log 1 plus something. So in order for me to get an x, then this will have to be x minus 1. But I know what is log 1 plus something. Okay, so I can just expand using that. Okay, just replace your something there, and then I will get your log x expanded about x equals to 1. So this is sort of easy because you can actually cancel off this thing, but you can actually do variation of this kind of what you call expansion of your power series. Probably you want to try what would be log x, the Maclaurin series for that. That means you find the expansion about x equals 0. Of course, the first order term will not be well defined because you get log 0. So that means you have to you have to look where precisely the log function is actually starts to be defined. That's why the right expansion for this is coming from this one. Okay, 1 plus x, because when you put x equals 0, then you have log 1. So here it has to come through some, it has to avoid the x equals 0 thing, and then you probably need the higher order terms. Okay, right. So here's another one, a cosine x. So the one that we have seen, the one that you're supposed to derive, okay, your cosine x is expanded about x equals 0. Now suppose I ask you to do cosine x expanded about a different point. Okay, so what do you need to do? So here it will be something like this. Okay, you need cosine x. You need to convert it in terms of the expansion about the point. Okay, so here is about the point x equals to 3 pi over 2. So I put x minus 3 pi over 2, but then you get a different function there. So I need to plus 3 pi over 2 so that it cancels off this 3 pi over 2. So I have that instead. Okay, and then what do you do with this is that you actually use the addition formula for your cosine. Okay, you can do this a bit more general if you want to, but then for example, I can do, say, cos x expanded about x equals to a. Then I would need to be able to find out what is cos a, what is sine a, and so on and so forth. Okay, right. What else? Applications. Okay, here's some interesting applications. How much time do I have? I have about 6 minutes left. Right. Here is sometimes when you do calculations using computers, sometimes if you do the whole function, it will probably take a lot of time. Okay, so sometimes what you do is to look at only lower orders of the expansion of those functions. So for example, here is the expansion for the exponential of x times cos x, which is given by that. Now you can actually plot this. Okay, when we plot, say, in this case, let me see. I don't know whether can you see the colors? Are you able to see the colors? Somebody?
Yes.
Okay. You can see that your actual function is in purple here. Okay. So the purple function here is the actual function. The one in blue is the how should I say? The one in blue is the order of your the approximate order that you take. For example, let me go up. If I take it to the linear order, then what do I get? I will get x plus 1. So that would be just a straight line. Okay. So if I say, okay, I want to up to a certain order, say x cubed, then it will, I think it's this one. Okay, it will give me that. And then if you go to higher orders, then you can actually see, okay, this one almost approximate. This is, I can't remember what order is this. Probably this the this is the third. Suppose this is the fourth. Okay, fourth order, and then fifth order, and so on. Okay, so you can see that this almost approximates the function already, but no, it fails at this point. And then the higher order one, oh, okay, it approximates there. So no, your approximation gets better, but it still fails at some point. But definitely you can see this part one, it already have a good approximation there. The one that fails is when x is negative. Okay. So you start to understand better how the power series start to approximate your function. Okay. So here is another one. And you can see always it's the negative one that gets, that fails in some sense. Okay. So depending on so in other words, there will be some interval over here, for example, there will be some interval here is that until probably here, no, because over here is probably, so in other words, if I want to know the function with respect to this interval, then I don't need to expand it too high. I can already, probably this is about the 6th power or something like that. Okay. And then using a 6th power polynomial is much more computationally cheap compared to trying to expand to infinite powers. So you can actually do those kind of things. Okay. All right, let me can see the whole thing. It also can see, okay, this one probably I want to do this in the next lecture just to see. Sometimes there are cases where even your computers might fail. Okay. For example, this function here, log 1 plus x divided by 1 minus x square root. Okay. And then take the difference with minus tangent x. Okay. Normal calculators, you can try this for yourself. Normal calculators might give you this answer, but the right answer is actually that. And you can see that it's really quite a lot of difference here. Here it's at 6.06, here it's 5.06. And the powers are quite small. Okay. So in these particular cases, you need to understand the behavior of the function, okay, because this one already almost approximate your tangent x. So you only start to deviate when it goes to very higher powers. Okay. So in other words, when you take a small value of x over here, then you need to know when precisely you want to take the approximation. Okay. So it's good to use this idea of power series to actually check for this. So the best way to do this is to evaluate this power series first, and then evaluate this power series next, and then after that only take the difference. You can see it's quite similar. Okay, the answers. So okay, I'll stop there today. Time's up. So now let me just mention. Let me just take the attendance first. Okay. So attendance. Oh, come on. Don't leave yet. Please, I'm taking your attendance now. Okay. Okay. I will be giving you a quiz sometimes, maybe during the weekend or something, so that you need to actually answer it. And then your first exercise or assignment, rather, probably early next week. Okay. So I think that's all for today. Thank you, everyone. Okay, bye. Bye. Bye.